My name is Kevin McAlay. I'm Vice President of Global Marketing for 3D Systems, based at our new facility in Rock Hill, South Carolina. 3D is a company based in the United States, but we have offices and facilities around the world. Selective laser sintering, like all of these processes, starts with three-dimensional CAD data. That 3D CAD data is sliced into thin layers, and that's the input to the selective laser sintering machine. In selective laser sintering, you have a container full of powdered plastic, and then you have a laser and scanning mirrors that allows you to move the laser beam across the work surface where you have the powder. And to build a part, you feed the slice information to the scanning system, and it scans the laser, which is a CO2 laser, across the work surface, and it selectively fuses or melts the powder wherever you have part cross-section. Once you've selectively fused all of the material in a particular cross-section, you then have new powder, which is added to the work surface via a counter-rotating roller. So once I've finished one cross-section, I lower the work platform by an amount equal to layer thickness, and I roll new powder across the work surface to create a new fresh powder layer, and then I scan that layer with my next data and selectively fuse wherever I have part cross-section, and I put in enough laser energy to adhere it to the layers beneath it, and I keep repeating that process until I've constructed my three-dimensional parts. We actually use the laser to raise the temperature of the powder from below its melting temperature to above its melting temperature, and strictly speaking, in sintering, you actually adhere materials together in the solid state below their primary transition temperature. So with selective laser sintering, the defining advantage is that you can melt materials that are engineering plastics directly in the machine and produce parts which are functionally equivalent to end-use parts in terms of their overall properties, including elongation of failure, toughness, and longevity. That is how they age over time. And so if I need a prototype that is going to be used and tested in a very functional way, let's say under stress at elevated temperatures, selective laser sintering allows you to make highly functional parts that can withstand the rigors of true functional testing. For direct manufacturing today with selective laser sintering, the primary materials being used are Duraform materials. And the Duraform materials are polyamide-based systems, both unfilled and glass-filled materials. And those materials exhibit very desirable properties with respect to toughness and aging. And they perform much like the end-use materials in many cases. As a matter of fact, in the case of the aircraft duct application I presented before, the materials, in fact, that were used in rotational molding and that are being used in selective laser sintering are almost identical materials. So it's made it a very transparent transition for manufacturers in that particular case. We also have a newer material called Duraform EX, which is a next-generation polyamide system, and it has enhanced toughness compared to the earlier generation Duraform systems, and in fact has elongation at failure and unnotched and notched IZOD values, which are actually as good as or exceed molded parts made from polypropylene ABS engineering plastics.
Here's a couple examples of parts that are made in our selective laser sintering process. An electrical connector made in two different colored dyed materials, but this will be used directly in an electrical application. Another similar part is made of three different pieces. Again, it's sintered polyamide powder, PA, and produced to be used in electrical applications as well.